Hello and welcome back to Probability Theory. And as you know, first I want to thank all the nice people that support this channel on Steady or PayPal. Now in today's part 8 we will talk about two important formulas, namely about the total probability formula and about Bayes' theorem. This formula of Bayes is so famous that we should immediately start with it. However, it's not so complicated at all because we already know the conditional probability of an event A under B, which is simply given by the probability of the intersection divided by the probability of B. And now of course we can also flip the roles and look at the conditional probability of B under the event A. Then we also have the intersection, but then we divide by the probability of A. However, the important part here is the intersection is the same. Hence with this part we can put both equations together, which leads us for left hand side to PA under B times PB, and on the right hand side it leads us to PB under A times PA. And in fact, this is what we call Bayes' theorem. In this order it's easy to remember because here we have the condition B and PB and here the condition A and PA. Okay, at the end of the video I can show you how we can use this formula. However, before we do this, let's talk about the law of total probability. It tells us which possibilities we have to split up a probability. So as always we choose a probability space given by a sample space omega, a sigma algebra A and a probability measure P. And now we want to calculate the probability of a subset A. So the question is, how can we split up P of A? Now one possibility would be to choose another set B. In the picture we can also visualize this maybe like this. So the set B is here and you immediately see how the set A is divided now. We get this because we have the set B and the complement of B. And of course both together in a union give us the whole sample space omega. Important to note here is this is indeed a disjoint union. Therefore this division here works no matter which event A we choose. And this is now what we can put into a formula. So we have P of A where we can write A as a disjoint union, namely the union of the upper part here we have in B with the other part we have in BC. And because this is a disjoint union we can use the property of the measure and write it as a sum. So we have the probability of this intersection plus the probability of that intersection. Now as before, an intersection we can rewrite as a conditional probability. For the first one we write PA under B times PB. And for the second one we use the same formula but now with the complement of B. So you see, this is a nice formula we can use to calculate the probability of A when we know these four probabilities here. However, the law of total probability goes even further. We can also deal with the case that we don't have only one set B but countably many. So we could have 2, 3 or even infinitely many. Hence we simply say we have Bi where I comes from an index set that is a subset of the natural numbers. And of course we have to generalize this property here. This means that the union of all these sets is equal to omega. And in addition, as before, it needs to be a disjoint union. Now let's also visualize this in a picture. There's our sample space omega again, and now we don't just find one set B but a lot of them. For example, such a decomposition of omega could look like this. And here please don't forget, it's possible that we have infinitely many sets Bi, therefore in this picture they would get thinner and thinner when we go in this direction, for example. Of course there are a lot of possibilities to visualize this. However, the important part here is that we also have a set A of which we want to calculate the probability. In fact, this now works exactly with the same steps as before. So first we can write the set A as a disjoint union. Of course, this is again the intersection with the Bi's, which means in the picture we just put all these parts here together. Okay, then because it's a disjoint union, we can use the sigma additivity of the measure. So we get out this sum for the probabilities or a series when we have infinitely many. However, in both cases we can use the conditional probabilities again. So we have the sum of PA under BI times the probability of BI. Now this formula here is indeed the general law of total probability. And how we can apply this we will see in the next example. Actually, this is one of the most famous examples in probability theory. It's the so-called Monty Hall problem. And because it is so well known, I don't want to go into the whole history and the details. We just use it to compute a probability with the two laws above. However, I still have to explain how this whole puzzle works. So we have a game show with 3 doors, where there is 1 door with a car behind and 2 doors with a goat behind. And now let's assume that the car would be the better price to win. Okay, then the game works in 3 steps. First, you pick a door. Let's say you pick door 1. Afterwards, in the second step, the showmaster always shows you a goat. So he opens one of the 2 remaining doors. And maybe let's say here he opens door 3. And then in the last step you have to do your final pick. So you can either keep the original door or you can switch. And now I can already tell you, switching has the higher probability for getting the car. Therefore, if you want the goat, you should stay at the original door. However, no matter what you want, we can calculate the probabilities now. Here, please note the names for the doors are arbitrary, so we can call the first door we pick just 1. Moreover, we need some names for the events we consider here. Here, Cj should be the event that the car is behind door J. In addition, Sj should be the event that in the second step, the showmaster opens door J. Hence, we already know some conditional probabilities. And in order to make our life a little bit easier, let's only consider the case that the showmaster opens door 3. The other interesting case with S2 can be described in the same way. Okay, so in this case, we already know some conditional probabilities. Namely, the probability of S3 under the condition C3 has to be 0. The showmaster will never show you the car in the second step. He always opens a door with a goat. Therefore, we also know the probability of S3 under the condition C2. Because, this is what I told you, he opens one of the 2 remaining doors, never the door you picked. So in this scenario here, he does not have a choice. Hence, the conditional probability here is 1. Then, the last remaining case would be where he has a choice, therefore we say the probability is 1/2. So you see, just by knowing the problem, we already get a lot of information. And please also note, here we didn't define a sample space, a sigma algebra, or even a probability measure yet. Simply because we don't need it, we just want to know what happens in any probability space when we have these conditional probabilities. Indeed, this will be our last step here. So we want to know what is the probability of getting the car when I switch the door in the third step. And this is exactly given by this conditional probability. Now, maybe not so surprising, now we can apply Bayes' theorem here. Please recall what it tells us. We can exchange the order in the conditional probability here when we multiply with the probability of the last part. However, we don't have it on the left hand side, therefore we have to divide here by the probability of S3. Therefore, often you see Bayes' theorem in this formulation. Okay, now here on the right hand side we have a problem, because we don't know what P of S3 is. However, we have all the conditional probabilities here, therefore we can use the law of total probability. Hence, in the denominator we get a sum with 3 parts. Namely, we sum over P of S3 under Cj times the probability of Cj. And there we can put in our conditional probabilities. Okay, then let's start in the numerator. This probability here is 1. And the same we find here in the denominator as well. Then on the right hand side we find the conditional probability that is 0. And then the last remaining one on the left is 1/2. Okay, now you see, the last ingredient we need would be the probability of C2 and C1. And there of course we have the assumption that this is the same probability. So we assume a fair game, each door has the same probability for getting the prize. And by having 3 doors, this would mean we have the probability 1/3. Okay, now we have substituted everything with numbers, such that we can simply compute. And we get out 2/3. So indeed, we get out the result that in this scenario, switching is beneficial. However, of course, the goal here was not winning a car, but rather seeing the application of Bayes' theorem and the law of total probability. Okay, with this I think it's good enough for today, and I hope I see you in the next video. Have a nice day and bye!